Our next goal is to develop a robust loss function for heterogeneous treatment effects. Once we have it, we're going to be able to use it for treatment effect estimation in a generic machine learning setup. Just to go over our statistical setting, it's the same as always. We have x's, y's, w's. W's are treatment, y's are outcomes. Outcomes are generated in terms of the potential outcomes model, as usual. And what we want to do is estimate the conditional average treatment effect. That is the expected difference in potential outcomes conditionally on features x. In this setting, to do this, we're going to assume unconfoundedness. That is, that treatment is as good as random, conditionally on covariance x. And the propensity score, that is the probability of being treated conditionally on x, is going to play a central role. So here I'm going quickly because this builds on things we've already seen last week. But essentially under unconfoundedness, you can always write that the expectation of y given x and w is mu0 of x, the baseline effect, plus w times tau of x. That is, your outcome is the baseline, your expected outcome is the baseline effect, plus if you're treated, also the treatment effect. And since this is an expectation, you can also write it that yi is actually mu0 of x plus w tau plus epsilon I for some epsilon implicitly defined in terms of potential outcomes, where we know that the property of epsilon is just that it has mean zero, conditional on x and w. Like when estimating constant treatment effects, we're going to want to re-express this so that yi is m of xi plus wi minus the propensity score times the Kate plus noise, where e of x is the propensity score, m of x is this kind of marginalized baseline effect, your best prediction of y given x without knowledge of treatment. And once we have this, we're going to land on essentially Robinson's transformation like before. That is under unconfoundedness, y minus m is equal to w minus e times tau of x plus mean zero noise. What we emphasized last week is that if you were to assume further that tau of x equals theta is constant across all units, then essentially up here, you could replace this tau of x with just a constant theta, and you could estimate this constant treatment effect parameter by regressing y minus m on w minus e. We talked about properties of this estimator, and we found that kind of this residual regression, even if you have to estimate m hats and e hats reasonably accurately using some machine learning method, this residual regression is going to give you a root and rate central limit theorem and kind of very good guarantees for estimating theta because of kind of its nice robustness properties. The difference between last week and today is that now we're not going to assume that the treatment effect function is constant, that tau of x is theta for all values of x, but we're going to let tau of x vary because, right, we want to estimate this tau of x function more broadly. And here, essentially the useful thing to notice is that, of course, we can't do a global regression to recover kind of the single parameter theta anymore because there is no single parameter theta anymore. But what you can do is imagine kind of filtering for each value of x only to the samples at x, and then regressing y minus m of x against w minus e of x only for units with a specific value of x. And kind of what this thought experiment shows you is that by Robinson's transformation, tau of x, the Kate function, is actually the minimizer of this following quadratic function. So tau of x is the minimizer of this function L, where L is y minus m minus tau times w minus e of x squared. Essentially, what this is telling you is that if I fix x, and now at a fixed value of x, I ask you to predict y minus m from w minus e, then tau of x is the best is the best thing for doing so. So here I just want to emphasize that this kind of minimization is to be taken non-parametrically. That is, tau is no longer a number that minimizes some objective function, but tau is a function of x, where at each value of x, tau of x can be unrestricted, but it actually turns out that the Kate function, the thing we want, is the thing that over the population at each value of x minimizes the expectation of this loss function, L, or this quadratic function L. So it might seem like I haven't done much here. I just took the Kate representation, I rearranged it a little bit, and I noted that from this rearranging, we see that tau of x can be characterized as this minimizer of this quadratic functional. But it turns out that actually, if you're thinking about estimating tau of x, this is super helpful. And just to kind of give one example, let's think back to the lasso. So you saw this a few weeks ago. The lasso, usually we think of it as a method for prediction. We want to use the lasso to predict y from x. And we're going to use the lasso if we think that there's a linear model that's good for predicting y from x. But this linear model may be very high dimensional. The number of the parameters in the model, p, may be much larger than n. And in this setup, what the lasso does is it tries to predict y from x. So it minimizes a squared error loss, but it doesn't kind of, linear regression would only minimize this red thing. So it actually kind of finds the beta that predicts y from x the best in sample. But the lasso does something else. It adds this L1 penalty of beta to the objective also, where kind of what this is saying is it's looking for parameter vectors beta that predict y from x well, but kind of with a preference for simpler parameter vectors beta that have small L1 norm. There are many reasons to like this. Kind of putting this L1 norm here preserves sparsity, and it makes sure that kind of predictions is kind of good prediction is still a meaningful objective in high dimensions. But anyway, so this is the lasso. This is something people do a lot. Now, a natural follow-up question would be, let's say we're still in high dimensions, we still like linear models, but we don't want to just have a high dimensional linear prediction model. We now have x's, y's, and also treatments w, and we wanted to fit a Kate function, tau of x, where now tau of x is linear in x, but where x is high dimensional, so beta is a high dimensional vector. How could you fit this beta? This might seem like a tricky problem that you kind of have to think about for a long time to come up with appropriate methods. But actually, kind of once you realize that machine learning is about minimizing loss functions in some specific way, so kind of any specific machine learning algorithm should combine a loss function and kind of an algorithm by which you minimize it. Well, how do you think about the lasso? The lasso, here's the loss function, that's in red, and the thing in blue, that's like the algorithmic choice that makes it the lasso. You don't just kind of minimize the loss directly, but you fit a linear model and you L1 penalize the coefficients for sparsity. So what are we going to do for fitting Kate? Well, again, we want to run something like the lasso. So we're going to linearly parameterize our Kate predictions. Our Kate predictions are going to have the form x beta, and we're going to put an L1 penalty on the parameters beta. On the other hand, what are we going to use the loss function? Well, instead of using squared error loss like for prediction, we're going to use this loss from the previous slide I just described. That is kind of the thing you get out of Robinson's transformation. And essentially the claim is that, look, now the problem is essentially solved. You want to have a lasso-like estimator for the Kate, just run the lasso, but swap out your squared error loss for this Kate appropriate loss function, and you're in business. So, okay, there of course is one wrinkle to the problem that is kind of a wrinkle we've seen many times, which is that this loss function here, it depends on, can remember that this loss function is something that you'd want it to just depend on the data, x, y, w, and tau, the thing you want to estimate, and then you'd kind of want to find tau that minimizes the loss function averaged over the data with some regularization. But the problem is that in this loss function, you don't just have your x, y, w, and tau, you also have m and e, these kind of other functions that are just hanging out there. You're not interested in them, but you can't form the loss function without having them. And this is a problem. If you knew m and e a priori, then what I just described would have been exactly the same as what we saw in the earlier slides with inventory management. That is, there was a task, there was a loss function. You learned your decision rule by minimizing that loss function, and there's nothing else to say. But here, we can't actually form our loss function because the loss function depends on these m's and e's, which are unknown. And so what are we going to do? I think given the theme of the class, it's quite clear what we should do. That is, we're going to need to first somehow estimate m hats and e hats using some first step regressions. This is what we did for estimating constant treatment effects using Robinson's method. This is what we did in causal forests. This is what we're going to have to do again. And then the question is, can you still learn Kate using tau, using this kind of loss function if m hat and e hat were learned from data? But luckily, happily, the answer is yes. So this is an algorithm referred to as the R-learner, kind of extending the alphabet soup for different types of algorithmic strategies you can think of for generic machine learning based Kate estimation. And the R-learner involves first fitting m hat and e hat by learning to predict y and w respectively from x. And then what we're going to do is we're going to form this loss function here, but with cross-fitted plug-in values of m and e. And then we're going to fit tau hat by minimizing this loss function with plug-in values of m and e. And this term here, this lambda n, this is kind of some type of regularizer on tau. The regularization could be explicit. Like if it's the lasso, then tau is actually going to be able to form x beta, and your regularizer is going to be an L1 norm of beta. But in other types of settings, like if you wanted to minimize this loss function via boosting or via deep nets, then this lambda n could be something much more implicit. For example, in deep learning, one common idea is to regularize a network using this technique called dropout, where you kind of during training randomly omit some nodes from the network. That gives you a type of regularization, but it's more implicit. But anyways, with this notation, I'm trying to capture both explicit and implicit regularization. And anyways, the formal result is, and I'm not going to go into it here because kind of just stating it is more technical than what I want to do now. But the point is that you get similar robustness properties as we saw with Robinson's method for constant treatment effects and as we saw with AIPW. That is, as long as you estimate m hat and e hat using reasonable accuracy, then your guarantees for learning the Kate using this kind of loss function are as good as you would have gotten using kind of a priori perfectly known m and e in the loss function. So the reason I don't want to talk about this is We haven't in this class talked about, say, optimal rates for estimating functions over non-parametric classes. So even kind of to talk about what would be a good rate of convergence with tau hat under different regularity assumptions on the function class containing tau of x, that would be a long aside from the class. So I'm not going to go there. But the main point is that if m hat and e hat are reasonably accurate, then you can get guarantees for tau hat that are as good as though you had plugged in the true values of m and e into the loss. And it's possible to get guarantees for tau hat, where tau hat converges in squared error loss much faster, an order of magnitude faster than m hat or e hat do. So this is a nice property. This is a property we saw out of, say, constant treatment effect estimators. This is not a property that any of the meta-learners we talked about last week have. So the ST and X learners in general are not going to have a property where they can achieve faster rates of convergence for the Kate than they do for their nuisance component estimates. But so anyways, the claim is that kind of the R learning framework, the claim is that you can essentially do most things you want to do in the world of Kate estimation by just first estimating m hat e hat, then forming this as your loss function, and then just applying machine learning generically using this loss function. In the next part of this lecture, I'll go into more details of how you can use this loss function for model choice, for model validation. So you can use this loss function for cross-validation or for comparing causal forest or the X learner, for example. But in this segment, I'll focus on kind of using this loss function for just kind of learning tau directly. That is, we're going to try to get tau of X by minimizing this loss function via different means. And okay, just one example showing kind of a semi-synthetic example where we see kind of the different trade-offs and choices involved in doing so. So this is an example motivated by this paper by Arsenault et al. On the effect of get out the vote calls on turnout. So we're going to take the real data. This data set has confounding, essentially because, and it's documented in the paper, in some districts you were more likely to get called than in other districts, essentially, if based on the competitiveness of the election. So it has a selection of unobservables. I mean, that is kind of, you need to control for some x's to get rid of that. But what we know also is that there's essentially no treatment effect. This is because, kind of, and this is the point made in the paper also, this paper is trying to measure the effect of one get out the vote call on turnout. And for all intents and purposes, right, like one phone call, like think about how many phone calls one might get during a competitive election. The effect of one phone call alone is essentially zero. So the main point of the paper was that here's a setup where obviously the treatment effect has to be zero, but if you don't control for compounding carefully, you'll find something that's not zero. But anyways, for our purposes, what we're going to do is we're going to assume, we're going to take the real data, assume that the treatment effect is actually zero in the original data, and then we're going to spike in a little bit of synthetic treatment effects by strategically flipping some outcomes. So now we've spiked in a treatment effect, and the question is, can we use various methods, machine learning-based methods, to recover it? And so here you see a histogram of the magnitude of the Kate we've spiked into the problem. And what do we need to do to carry this out using the R learner approach? So what we're going to do is first we need to learn m hat and e hat, that is to predict y and w from x respectively. Then we're going to need to combine all this into the R loss, and then we're going to need to run some third machine learning step where we use the R loss as the loss function for learning. So first, we need to fit E hat and M hat, of course. And here, for both tasks, we tried both the lasso and boosting. And in both cases, we kind of cross-validated to see which one was doing better. And in both cases, cross-validation told us that boosting was more accurate than the lasso here. So we used, so then we got cross-fitted E hat and M hat estimates from boosting. Then in the second step, what we're going to do is we take the R loss or the R objective, and we're again going to try to minimize it using lasso or boosting. So for lasso, we're going to run lasso on the R loss objective. So we're going to do just what I described earlier. That is, we're going to do this, except here, instead of using the L that depends on the true unknown M and E, we're going to run this with plug-in values of M and E. We're also going to consider boosting. If you know what boosting is, then we're just going to run boosting as you know it, but we swap out the squared error loss with R loss. If you don't know what boosting is, well, then you can just know that if you wanted to do this, all you'd have to do is read about boosting and then swap out the loss function. But anyways, we ran this, and then we cross-validated again based on now the R loss, not squared error loss. And here, cross-validation prefers the lasso. So we end up getting M hats and E hats out of boosting, but a final fit for tau of X that's going to be linear in X and fit by the lasso. And so now what's nice is that this is a semi-synthetic kind of in the end. We know what the true tau of X was, so we can see how well we did. And we were right. Our mean squared error kind of scaled up by 1,000 for the R lasso was 0.47, whereas kind of R boosting would have gotten 1.23. So kind of cross-validating on the R loss not only helped us train the lasso well, but helped us correctly notice that the lasso was doing better than boosting here. On the other hand, other things you might have tried here is you might have been interested in kind of just kind of fitting everything by a single lasso, something like an S lasso. Here, that did worse than the R lasso, or you could have just kind of thrown, I haven't talked about it here much, but BART, it's a popular Bayesian tree approach. And here, it also is less accurate. So the main point is that, again, this kind of R learning approach is flexible. And once you're using it, everything just looks kind of very familiar from kind of a machine learning workflow. You pick the best E according to squared error loss. You pick the best M according to squared error loss. You pick the best R according to tau loss, and then you proceed. So this is one thing you can do. Another kind of nice application, just to show that kind of once you have a loss function, you can really do a lot of things with it. So one popular idea in machine learning is what's called stacking. Stacking starts from kind of, you have capital K, different estimates. You say you have kind of K experts you hired to give you K estimates, and they all give you different estimates. And now you don't know which one to pick. And really, you think maybe all your experts are onto something, and maybe they're onto something slightly different. So you'd want to find a consensus estimate that kind of averages all of your experts' predictions. And let's say you wanted a consensus estimate that's here, it's some offset plus a positive weighted average of all the tau Ks. So you don't want to insult anyone. You don't want to give any of your experts negative weight in your model, but kind of what this thing could do is it could just kind of say the fifth expert is the best, so just set tau of x to tau 5, or it could kind of give some positive weight to a number of different experts. And then, of course, if you want to stack, the remaining question is, how do you pick these weights alpha k? How do you choose how much weight to give each expert? And this might seem like a difficult problem, but again, once you have a loss function for Kate, it's very clear what to do. Just write tau of x in the form as usual, and then fit these parameters by minimizing the loss function for Kate. And here, the kind of only difference from what we do usually is that there's also this constraint saying that here the parameters we want to learn are these alphas mostly, and we're going to add a constraint that these alphas should be positive. Solving this optimization problem, this is going to be kind of a quadratic objective with positivity constraints. It's a quadratic program. If you kind of want to learn how to solve this kind of optimization problem, you could say take a class in comics optimization. But the point is that once you have this loss function, kind of what to do is immediate, and then kind of all the difficulties are just routine machine learning type difficulties. Say, how do you solve a comics optimization problem? And just kind of to see this working. Again, here we had one example where there's a simulation study. I won't go into details here, but kind of this paper, there's a reference on the last slide to this one if you want to read more. But essentially, in a pair of simulation studies, we tried fitting causal forests. So this is kind of complicated forest-based method, right? That like does a lot of things. It causal forests, like the R-learner, are built on this Robinson-based insight, but of course, causal forests aren't a direct consequence of kind of Robinson's transformation. There's a lot more going into it, kind of how exactly we chose to implement the algorithm. Then I tried running something else here. I tried running BART. BART is, like I mentioned earlier, it's another popular tree-based method, but kind of based on hierarchical Bayesian modeling. So algorithmically, it's very different. And tried fitting causal forest, tried fitting BART. Which one is better? Well, at least in this one, what's interesting is you see I tried stacking causal forest and BART using the method from the previous slide. And what you see in green here is the mean squared error for the stacked estimator. It actually ends up being better than either causal forest or BART on their own. So I guess this makes a couple of points. First, in machine learning kind of is inherently an engineering focused area. So what's going to work best? It's kind of unpredictable. The kind of best thing to do generally is to be empirically driven and try a bunch of things and see what works. But then the other thing is, in order to be empirically driven, you need a criterion of success or failure. Otherwise, you're kind of flying blind. And the claim is that for Kate estimation, the R loss provides one such measure of how accurate a Kate estimate is that you can use for many purposes, ranging from learning to model averaging.